A very warm good morning to one and all present over here class. Welcome to the digital platform of APS. Now this is Pawan Kumar. Today I will discuss some proof related to modulus of complex properties of modulus of complex number. So see, some proofs related to properties of modulus of complex number. Some proof related to properties of modulus of complex number. Now see, now first proof is if mod of z is equal to 0, then real part of z is equal to 0, comma, imaginary part of z is equal to 0. So see its proof. Let z be any complex number such that z is equal to x plus iy for all small x comma y belongs to real. Now since it is given mod of z is equal to 0, this implies we can write root over x square plus y square is 0. Now this one we can write x square plus y square is equal to 0, and this implies we can write x is equal to 0 and y square will be equal to 0. Now we can write y is equal to 0, this is x, and y is equal to 0. Now this is the real part of z is equal to 0 and imaginary part of z is equal to 0. Now this is our proof. See, now I will come to the second proof. Second proof is prove that mod of z is equal to mod of conjugate of z is equal to mod of minus z. So all values are equal. We have to prove this proof. So let Z be any complex number such that Z is equal to x plus iy for all small x comma y belongs to real. This implies negative of Z we can write minus x minus iy for all minus x comma minus y will belongs to real. Similarly, conjugate of Z we can write x minus iy for all small x comma y belongs to real. So through this first expression we can write, here we can write mod of Z is equal to root over x square plus y square, and this is minus time mod of Z is equal to, this is root over x square plus y square, because minus x whole square plus minus y whole square result will be same. So this result will be the same. So from this and this means Z, mod of Z, mod of minus Z and mod of conjugate of Z. We can consider equation 1, 2, 3. We can consider equation 1, 2, 3. Consider this is 1, this is 2 and this is 3. Now we can write from equation 1, 2 and 3. What we can write? We can write mod of Z is equal to mod of minus Z is equal to minus time mod of Z. So this is our proof. Now this is completed. Hence proof. Hence proved. Now see, next proof. Next proof is third proof. So our third proof is prove that Z into Z bar is equal to mod of Z whole square. So we have considered one complex number Z. So now Z is equal to what we can write? We have considered Z is equal to x plus iy for all small x belongs to real and small y belongs to real. Now Z bar we can write x minus iy, and mod of Z we can write for all small x small y belongs to real, consider equation 1 and consider equation 2. And mod of Z what we can write? Mod of Z we can write root over x square plus y square for all small x comma y belongs to real. Consider equation 3. Now suppose you are going to multiply equation 1 multiply by equation 2. So z into z bar is equal to x plus iy into x minus iy, and this result we can write x square plus y square. And this result we can write x square plus y square power 1 by 2 to the whole power 2, means root over x square plus y square power 2, and this is the value of mod of z whole square. This is the value of mod of z whole square. So we can write z into z bar is equal to mod of z whole square. Now this is our proof. This is our proof. Can see. Now I will come to the next proof. The next proof is prove that minus time mod of z is less equal to real part of z is greater equal to, or this is greater than or less than mod of z. So and second is minus mod of z this is our proof. Prove that. These are two statements and we have to prove. So you know let z be complex number such that z is equal to x plus iy for all small x belongs to real, small y belongs to real. Now mod of z, what we can write? Mod of z result we can write root over x square plus y square. Root over x square plus y square. Now minus time mod of z we can write minus time root over x square plus y square. And in this expression the real part of z is x and imaginary part of z is equal to y. So from this expression it is clear, or we can write x is always greater equal to minus time root over x square plus y square is lesser equal to root over x square plus y square. This implies what we can write? Minus time mod of z is lesser equal to, this is real part of z and this is mod of z. Now similarly, minus time root over x square plus y square is lesser equal to y is less than root over x square plus y square. Now this implies what we can write, minus time mod of z is less equal to, and this is imaginary part of z is lesser equal to mod of z. Now hence proof. Hence proved. Now I will come to the next heading, existence of identity element for multiplication. Existence of identity element for multiplication. See, existence of identity element for multiplication. For multiplication. Now, how we can see? What we can write? The complex number 1 here we can write the complex number 1 is the identity element for multiplication. Identity element for multiplication. So what we can write? For any complex number z, for any complex number z, what we can write? Z into 1 is equal to z is equal to 1 into z. We have to show. So see, z into 1 we can write x plus iy into 1 plus I0 for all x comma y comma 1 comma 0 belongs to R. And this one we can write x plus means when you will multiply x into 1 or result, you will get the same result, x plus iy, and this is z. This is z. Now 1 into z, we can write 1 plus I0 into x plus iy. It's a result. Also you will get z. So from equation, consider this is z into 1, this is 2. So from equation 1 and 2, z into 1 is equal to z is equal to 1 into z. This shows the multiplication, or 1 is the multiplicative identity in C. One is multiplicative identity in C. Now this is completed. Now existence of multiplicative inverse. Come to the next heading. Existence of multiplicative inverse. Existence of multiplicative inverse. Now see, existence of multiplicative inverse. So what we can write? For any complex number z, for any complex number z, there exists a number z inverse such that z into z inverse is equal to 1, or z inverse into z. This is the result. So see, let z is equal to x plus iy. So Since z into z inverse is equal to 1, you know, so x plus iy into z inverse is equal to 1. Now z inverse result will be 1 upon x plus iy. Now z is inverse is equal to 1 upon x plus iy. This implies z inverse we can write x minus iy upon x square plus y square. After rationalizing, now this expression x upon x square plus y square plus I minus y upon x square plus y square is the multiplicative inverse of z. Z inverse is the multiplicative inverse of z, and it is its value. Now this is completed.